All right, we're live. How's it going, everybody? Thanks for joining me today. Today we're going to be working on that 6-stage pipeline CPU in Minecraft. And the first thing I need to do is copy this into Minecraft here, just so I have a reference, so I'm not always having to come back to the spreadsheet. So in game, I have mapped out the instructions so far, just in terms of their instruction mnemonic. I'm not going to write the assembly format out because that's all in the document. I just want the bit fields. So we need to keep for all the ALU ones, we need like the top bit of the immediate to be like designated differently here. So I'm gonna get what is this? Magenta. Grab some of that. That goes to absolute value. We need it for AND, XOR, XNOR, and then shift. Okay, so that's going to say if it's a 0, then or 0 equals RS2, 1 is equal to immediate. And then this is going to be signed 15-bit immediate. And we're going to stack that. Hey, what's up, Crispy? 1, 2, 3, 4, 5, 6, 7, 8. We're going to stack that 8. Okay, so those instructions are easy to lay out. But now we have to do the shift instruction here, which means the 3 bits to the right of that are going to be lime. And those are going to be shift logical left, or shift left logical, shift right logical, and shift right arithmetic, like that. Then we have, oh wait, 1, 2, 3, 4. Well, we just have 4 bits left over here. 1, 2, 3, 4. Like that. So all these are not used. So we'll use like obsidian, or no, bedrock for the not used. And then here we'll use green. 4-bit shift amount. This is going to be 0 is equal to reg, or no, it's going to be equal to RS2, sorry. RS2, and then 1 is going to equal to shift amount. Okay, and now the next thing that we need is shift set less than, which is going to use the same format. The next 3 instructions will have the top bit used, the most significant bit, so of the immediates, and there's Pensy. So 0 is equal to immediate. Equal to RS2. Assign extended 15-bit address. should be a signed 15-bit, signed extended 15-bit immediate. Signed extended. Oh, then Pensy left. Okay. So for the absolute value, we don't need anything past RS2 up here. Yeah. Okay. Oh, an add vector doesn't need an immediate. It wouldn't make sense to use an immediate with a vector. You would just use add. And just use regular add immediate. You wouldn't need an add vector instruction for that. Now set less than and set less than unsigned doesn't need an immediate. So set less than unsigned here. Oh, this is signed or unsigned. 0 is equal to signed, 1 is equal to unsigned. There we go. Now we stack this once. Wait, what? Stack. Okay, there it goes. Then what else do we need there? Oh, underneath set lesson, we don't need anything in RS1 for the jump link. Source 1, don't need anything there. Then the next instruction here, we don't need anything here or here. And then the instruction below. That. Oh wait, no. And then oh shit. Chat, all those signs broke. Crap. Oh well. Zero is equal to RS2. 1 is equal to immediate. Stack, I don't know. And then now where isn't that true? For set less than, it's signed and unsigned. Equals set less than 1 is equal to set less than unsigned. Cool. Perfect. And there's basically the ISA laid out. We don't have an instruction for number 14 yet, so there can still be another instruction added. So now let's walk through what I have done so far. We've done all of the add vector, subtract, or absolute value, and XOR, XNOR, shifting, set less than unsigned, jump and link, oh. Yeah, we have done jump and link register. We've done jump and jump register, I believe. Yeah. Let's check out what we've done up here. So this instruction here is coming from this, where that glowstone is. This line here, which is instruction 9, which is set less than. Okay, sweet. We have the set less than. We've done at least up to instruction 9 there. But it looks like we've done jump and link register and jump register. But there's no write back to where we're gonna like put like value into a register. So the difference between jump and link and jump and link slash jump and link register and jump slash jump register is they both just jump somewhere, like just put a value in the program counter. But they also like have one difference. The value, jump versus jump register, the value that goes in the program counter is either from a register, like a value from a register, or it's an immediate value from like the code. So that's jump versus jump register. Then jump and link versus jump and link register is the same thing, where like you're jumping and the address that you're jumping to is either from a register, or which is jump and link register, or it's from just an immediate, which is just jump and link. The thing that's different about them is the fact whether or not you store the PC address as a destination or into the destination register. So jump and link stores the register address or the return address in the PC into a destination register, but the jump and link register does not. Or no, jump and link register does. Sorry, jump and link register does. Jump and jump register does not. So this one here, there's no RD enable, but you can see that it doesn't come to this line here because that's RD enable. And the RD enable line is what comes down here, and it tells me that I want to take a register, and it also comes over here. And enables the clock, or enables the data through here, through this pipeline stage. So the pipeline stage that will either have this in it, this register, or this register, and it's basically going to swap which pipeline stage it selects from, whether it's taking from the register or if it's taking from memory. Okay, so if we've done up to jump register, that means we have done to that. We need to then do the 3-operand branch and the 2-operand branch, but I think I was working on that. So we put in a 12. Yeah, that's this here. So we've worked on that as well. So that is our 3-operand branch. Just I'll write it here. Alright, so the 3-operand branch comes up here, and it's basically going to say, you're going to give it, by 3 operands, you have where you're going, and then the two numbers you're comparing. So you're comparing two numbers, if they're less than, or if they're, sorry, no, what is this? It is, if they're equal to or if they're not equal to. So you're comparing two numbers and seeing if they're equal to or not equal to. And you can check for either, for both of them. So that's what this is for. So if you look at instruction 12 here, we need to say that that first bit there is 0 is branch if equal. 1 is equal to branch not equal. So it's going to compare the two source registers, RS1 and RS2. Should probably stack that. Okay. So then we can swap between equal to or not equal to, and we can compare. We can say if these two are equal to, we will branch. If they are not equal to, then we will branch, and the address that we branch to will be an offset. So like the only place that we can branch from will be an immediate value, and that's just going to add some value, like some number, to where we are. So that's what a 3-operand branch is. It's an offset from where you are. So this way, like, the code can be moved anywhere around. And if it says I always just have to jump 3 ahead, it doesn't matter if it's on line 5 or if it's line 10. It's going to know I just need to jump 3 ahead. So you can shift that portion of the code around, and it won't screw with things. That's why it's all relative. Alright, so that's done as well, because if we put some value into this immediate, say torch, if we wanted to branch, we'd be taking PC plus 4 of where we are. So at 1 we're adding, well, PC plus 1, so we'll be at 1 we'll be adding 2, so let's add negative -2 like that, and it should have 0 then as a result. If it's taking PC plus 1, which is 1 plus 1, or no, it would be 0 plus 1, so we'd want to make that -1. Okay, no, yeah, because that's line 0, so the next line would be 1, so PC plus 1 from 0 would be 1. If you want to subtract 1 from that, you'd put in all 1s like that. Okay, so here's an example. So we're doing instruction operand 12. That means we're taking the sign extended 15-bit address, which means that most significant bit is just thrown away, isn't used. I guess I can use that for my equal to or not equal to. Yeah, maybe that would be smarter. Where is that come from? Equal to or not equal to? It comes from the top of the blue at that stage. But if I took it from here, that would be a lot easier. Yeah, that's what we're gonna do. They get their own boxes, and they need to. There we go. And Control C. There we go. I don't know why. Okay. It's basically what I want to do. So if I need to undo instruction or edit instruction 12 so that the most significant bit is where I grab that now. So I no longer want it from this. I want the most significant bit. And this is being done in the forward stage, so I want to grab the most significant bit. Instruction decode to forward and instruction forward to execute. That's where I want it. No, instruction sorry. That's instruction fetch to decode. This is instruction decode to forward. So I want it from here. I want it before it goes from forward to execute, which is this. So basically all I need to do three, two, one. I no longer need this fucking bus. Now it makes programming a little bit less ambiguous, even though you're never going to program in machine code anyway. Yeah, so I grabbed it in this stage after that register, which means I should grab the purple from after this register as well. And that register is right there, so perfect. So now I'm basically saying if the numbers coming through A and B are not equal, so the values coming through A and B right now are not equal, so the branch result will be true. And it's saying the branch is true. Or it's not really, yeah, so it's saying the branch is true. So, oh, so we have to do something with this. Okay, so if we need to then repeater. So what happens if the branch is true? Well, we need to tell the program counter to accept the value coming into it. So the program counter is way over here. And this is the PC source value that says the PC is a register, and that register is held right here. Now that register then comes back and increments by 1, comes back and feeds into itself. But if you disable the increment by 1 so that it never outputs, which is just by flooding both inputs with the output XOR here, that's what that line and that line do. When both of those are on, it disables the output here. And it can, then you would just enable this here, and it would take the data flowing through here and put it this way into your register. So that's how you perform a jump. You just take the data in here and put it into there. Or a branch, because the calculated address would come from this bus anyway. So the condition is true. We generate the condition in the forwarding stage. We should probably put a register It's after that light, but yeah, so it'd be birch. So that's our pipeline register for that. Now let me check my diagram, or a diagram. No, I want this. Okay. So the program counter address would then come, or the program counter address, it tells it whether or not the branch is true, and you generate your PC source. Let's see. Yeah. So this is what I need here. So this is my PC plus 1. It outputs this way. We can take our PC plus 1. And add to it. So this is slightly different. So like here is my instruction decode to forward, then forward to execute, and then after my forward to execute is my execute / memory stage. So out of my execute / memory stage, the result of the branch address comes through and comes back. So let me make sure that's right. So out of the execution stage, here the branch address comes over here and gets, yep, out of the execution, the branch address gets calculated and gets brought back. Okay. Which means out of execution stage, it should be told whether or not it takes that. So I have 20 ticks then from here to get this signal to the PC source, which is fine because we have 1, 2, right? Yeah, 1, 2, 3. I just got to get it to this green bus, I believe. Yep. Update PC with calculated address. Right? Where is this coming from? It should be out of the. It should be out of the. Yes. Okay. Perfect. It's out of the execute stage, which means I can literally just bring that orange bus onto this. And now it's saying take the branch address that was calculated. So that's 3, wait, 1, 2, I think that's 3. 1, 2, yeah, 3, 4, 5, 6, 7, 8, 9, 10, 11 synced. So not bad, 11 ticks or so to get this into there. We're still under that 20 tick margin. And then the other route that could take, it looked like it was from here. So out of that stage is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So yeah, synced both ways. Well, they're not both the same delay, but they're both under 20 ticks, and for the same instruction, it's the same speed. So nice. So that leaves us with well, now the two operand branches are less than or equal to 0, greater than or equal to 0. Shit. I think I would have learned by now. Signed and then unsigned for set less than. There we go. And then we need here. This is going to be the branch of equal. One is going to be branch if not equal. And then we have here 0 is branch of equal to or less than equal, branch of less than or equal to 0. 1 is going to be branch greater than or equal to 0. Okay. Since there's nothing filled in for this. This instruction isn't used yet or programmed to do anything, so we can leave that for like a later date to put something in here. And then we have load store, or maybe I should split it. Nah, we'll leave it the way it is for load store because it just makes it easy. That's how everything else is done. So Control C. 0 would be what? Load. And 1 will be store. There's no like worrying about register or immediate because it uses both. It uses a register as a base and then the immediate has an offset. So if you just didn't use the register, there's your offset. So you could just say whatever value you want, or if you just wanted a base, then you could do that, or then you could do both, like base plus offset. So that's the way that'll be implemented. So that we got to get there first. So we just did the 3-operand branch. Let's put in instruction 13. And then we're going to need just like a value out of one register. So I'll put in some bullshit value. And we're doing this, which means if there's a 1 up here, we're doing branch of less than, or branch of greater than or equal to 0. So if the source register here is greater than or equal to 0, so right now A is greater than or equal to 0. So it's using an unsigned, it's just for the greater than. It just knows that the value is bigger than 0. Well, yeah, it's looking at the most significant bit, obviously, yeah. So this is telling you greater than or equal to 0. So the reason it's saying that's greater than or equal to 0 is because the A bus here has data on it. If you look coming down here, there's data. And the B bus does not. The B bus has nothing on it. So since A bus is bigger than, well, A bus is the only thing we're looking at, and A is greater than, this data on there is greater than 0 because the most significant bit is on, then this is correct. But for instance, if we turn the most significant bit on the output, for instance, like just by doing this, then you'll see that it's no longer greater than, it's now less than. Okay, so this condition is true. So it's saying with this condition true, if this condition is true and the instruction is true, we need to then branch. So then we're basically going to say, when we're doing the instruction that we want, and the instruction and it's true, then we want to perform the branch. So we've got to say when we're on line 13 here, and we have to do it from this stage, mind you, because this is in the forward stage. So we have to do it here in the decode forward stage. So what I will do, alright, so we need to know where we're on that instruction, and then we also need to know what condition we're looking for. Whether or not we're looking for less than or equal to 0 or greater than or equal to 0. And that comes from the top of the of this right here, which is convenient as fuck. Holy shit, that's convenient. So basically, what I'd like to do is take this, and if this is on, so basically we're going to take this, and if this is a 1, we're going to, this is going to be a mux between these. That's how it'll work. So we'll say compare this, and then we'll have them output onto the same line like that. And then we can do this. If it's a 0, or if it's a 1, we want it to do greater than or equal to, we want it to select this one. So if it's a 1, we want it to be powering into a torch, turning this off, allowing that to be powered in. Oh shit. So now it'll select the top one. Else if it was 0, else if it's 0, it will take the bottom one. And now we're only going to select. Beautiful. Now here is our select line that we can say so we're not going to take either one unless the instruction is true, and then if the instruction is true here, So now we can say if instruction is true, then we can say we're looking at the most significant bit to tell us what the condition is, and we know what the condition is, and it's telling us that it's greater than or equal to 0 because that's what we're looking for, and it's true. But if that condition isn't true, we don't want to look for that condition and throw it on the bus. So now this comes from this state, this right here, which might be a little bit better to be brought. Wow. Wow. That just reached. That's crazy. How lucky are we? So that just reached. So we're on this instruction, which is allowing this data to be looked at. Cool. So now since this is true, we want to then take the address contained. Oh, we want to perform a branch, so we. Oh, okay. So we need to go back to instruction 12. We don't want to just take the address there. We want to add. We need to make sure that that uses the branch calculation here. So that means we need to be taking that value and putting it into here, which we're not. And that means we also need to be allowing that value into here, which we're not. Oh, maybe I should do it back here. So if I want to update the program counter with calculated address, but I need to know whether or not I'm using the so for a branch, okay, so for jumps I don't want to use that, and for branches I do. Oh, for jumps I don't want to use this. Oh, so for branches I just need to enable this. So for the branch here, when the branch is true, which is on this instruction here. So when the branch instruction is true, then we're going to take 1 and we want to put onto this bus. Wait, what the fuck? Why is that coming out? Oh, I'm looking at the wrong thing. There we go. So 1 is coming out here. Nice. Now if I add FF to it, we need to be saying for the branch, if that's true there, we need to then tell it to take the value from the PC offset, not the register value. We don't want it to take the value coming out of this register, which happens to be 0 right now. Why is there no? Oh yeah, that's right. Okay. So the branch instruction needs to flip that as well. branch instruction needs to flip that. During the execute stage. This is latched into the execute stage there. Yeah, so this needs to come from the execute stage. According to this diagram, it would have to come from the execute stage. The execute to memory stage. Wait, what? Ah, shit. I need to delay all of that by an extra pipeline stage. Oh, no. My diagram did not take into account for that. Alright, well, that sounds like a bitch. So let's take a hit off a bomb, calm down, and think about how we're actually going to do that. See, this is what's hard about pipelining, is you need to keep track of all your stages. And I'm not going to let a little detour throw me off. That wouldn't be very cool. That wouldn't be very cash money. This weed is pretty cash money though. Anybody in chat right now? Oh, excuse me. We got any viewers? Let's check. Got 4 concurrent viewers, hell yeah. Just gonna pack some weed and fix this dilemma. Okay, so I need to think about this. Why in MIPS do they have to do what they do? So like, I calculate my branch results the stage before the ALU. I'll calculate it in the forwarded stage. So I have instruction fetch, instruction decode, instruction forward, instruction execute, then instruction execute, instruction memory. Well, I guess if it's calculated in the forwarding stage, it should be forwarded to the execute stage and then come through. So the branch result needs to be not from the memory stage, but from the execute stage. So I should have my colors used here. Yeah, so I should be looking for it from that stage here. So for instance, we calculated our branch address and it got locked into that stage. Perfect. So our branch address got locked into that stage, which means we did that correctly there. So that means what we need to do is the control signal here not only needs that pipeline stage, but it needs this one as well. I'll get a sign. Execute /mem stage. Alright, so we put it in that bus. So now if we do a branch condition, the address that goes on there is from, alright, what about a jump? We should go back and redo the jump as well. So the jump, that's instruction 10 and 11. Instruction 10, put in a destination, put in no source 1, a source 2. We tell it whether or not we're taking the immediate or register. Alright, so first I guess we'll tell it we're taking immediate. Like that. Okay. So that should be doing jump and link, and the value that goes to the program counter will be told not to use this here. So it's not taking the +1, it's just jumping to the address contained here. And since we're doing jump and link, it's from the immediate, not from the address, not from the register. Okay, so then it's just taking that immediate address and it should put that on the PC bus here, which it does. But the control signal how is that control signal generated? Is there any control signal that has to come over to here? There isn't, because we're not telling it to do that. So since we don't have to actually add a, we don't have to screw with the program counter. We don't need a. It's only the branches that will have to flip that control line. So we don't need to pipeline that control line there because it's not going to be there. Jump and link, all that does is it takes the immediate value, doesn't use, it takes the immediate value, adds it to what the fuck does it do? What am I thinking of? Jesus frickin' Christ. Jump and link does not have to affect the program counter in a relative way. It has to override it. And in that sense, we don't have to use the branch calculation, which would have to be done in the execute stage. So since, as long as we forward the results from the birch stage to the acacia stage, so basically all that we have to do is forward the results from the birch stage here, yes, through this to the acacia phase. Okay, that's fine. So I think jump and link register, jump and jump register are fine. It's now going to be the 3-operand branch. So if I go back to 11, That was 12. So go back to 12. Alright, so run instruction 12. We don't have a destination register. We're going to have two sources. We're going to tell it whether it's equal to or not equal to. We'll tell it, oops. We'll say it's not equal to. We're going to say if these two values are not equal to, then we're going to branch. And that should be calculated in the execute stage. Doing 12, right? Branch. Oh, we're telling it equal to with a 0. So then if we tell it, if we give it a 1, that'll say not equal to, and then it'll be true. So the branch says it's true here. If the condition is true, we calculated it out of this, yeah, so then it needs to be sent into the birch stage. Oh no, this needs to be the birch stage here. Ah, okay. Or the acacia stage. Like that. There we go. But that means this needs to be coming from the execute/memory stage. And it's coming from the forwarding stage. Which means this as well needs that same thing. So now we have the pipeline stage for all of that. Because this needs to, it comes from the forwarding stage, and it needs to tell it here whether or not it's taking it from this forwarding stage as well. So that's the right thing. So from that forwarding stage, we calculate the forwarding stage, which says whether or not we used to calculate the branch. Branch is calculated and latched, and then the next stage it gets forwarded. Okay. Beautiful. Fucking beautiful. Let's have some brownie. Oh, how's it going, Kay? You're watching me while doing an exam. What exam are you doing? I was gonna ask how you're able to watch me while you're doing an exam, but then again I realized that everything is like online now, so like makes sense. This brownish is good. If this wasn't color coded, I would be so screwed. So the branch will always take a PC value. We'll always take an immediate value, but we'll never use a register. It's only the jump that uses this here, and it looks like that's configured already. So, yay. One less thing I have to do now. Yeah, so now I guess we do the two-operand branch and see where that control line needs to come from. It'll be from up here. I think all I have to do is just like make that the bus for it, because then it would have to do everything the same way. I wonder if that will work. Yeah. So if I change it to the next instruction, it's a single operand, which means remove the second one here. And now we're telling it that it's greater than 0. So it should be true. That number, we're asking if that number is greater than 0, and it's telling us it is. So this should then tell us, come over here and branch. Oh, and that's cool, because I could literally just then excuse me. Yeah, whatever. So now it's telling me that the condition is true, and it will do the same, everything it did before will be the same. It'll say update the PC with the calculated address, and it'll also make sure that we branch relative by calculating the relative address. Jumps are not relative, so we don't want to use this adder. So we disable the other input. So we still use the adder, but we just add 0, whereas this time we use the adder and just add the other number. Beautiful. But it's not working. Did this work on before? I don't know why it's not, but I don't know if I put the control line in for it on this instruction either. Yes. No, I didn't. So I need to select this. Oh, it is done right now. Oh, never mind. Wait, what? So most significant bit's just able to come over here and select. Oh, it's whether or not this right here is on or off. Yeah, that comes from here, which tells it what the instruction is. What instruction? It's either jump and link or jump. No, it's jump register, yeah. Jump register, jump and link register. Those four instructions use this line. It comes down here and it says if I'm using that jump, then I want to read the register address. So is this wrong? Why is there an inversion? Oh, I need to be saying disable it when I'm not on that instruction. Or I need to say when I'm on that disable. Okay, I need to disable both. Okay, I see. Okay, so what that should do is disable both, which it does, unless I want it on. And the only time I want it on is when I'm doing is when this instruction is on, for instance. One of these is when this instruction is on. So we could say if this instruction was on, then it would allow the immediate through. Alright, I have to go back through and make sure this works now for jump register, the right condition for the jump register, jump link register. So we need to go to instruction 10. We need to say destination register. We need a second source. We don't need a, yeah, we need a second source, not a first. And if this is a 0, then it'll take the immediate. And then if this is a 1, I would take the register value. Okay. So it's taking the immediate. And why is it taking the immediate? It's because I put a 0 there, and that's what I wanted. Yep, 0 is the immediate, 1 is register. So if I do that, it puts the 1. Nice, okay. Now I go to instruction 11 and hopefully it should do the same. I don't need a destination. Don't need a source 1, I need a source 2. And then 0 is immediate and 1 is register. So the 0 is immediate, so that should be putting an immediate here. Yeah, and it's blocking that side, perfect. And then 1 should be putting a register. And there's no value on that register. Why? Because it's the second source, and the second source has nothing on it. I believe here. Yes, if I put let's say a value of 7, just to have something on the second source. We should see 7 come through. Yeah. Okay. Cool. Very nice. Now that all works. So now we can move on to back to instruction 12. And I'm going to take another hit. Okay. We're doing branch. We want to do what? Branch equal to. No, not equal to. And then we're going to add this value to the program counter, so the output of the program counter should be 0. So let's see what happens. Telling it to branch not equal to. What's coming here and it's saying it's not equal to. The branch is true. Calculated that in that stage. Would come over here and tell it that it needs to allow this line. And then it would calculate this value and latch it in this stage at the same time that the flag also gets latched in this stage to tell it to come over here and then update the program counter address with the value that just got latched into the program counter value that just got updated. And so now this is telling it to swap the value that comes in. And so now you'll see that this is being forced to be zeros all on the output here. And then what it's doing is allowing this open and taking the value in, which, you know, 1 plus -1 is then going to be, wait, what? It should be throwing out +1 over here. Yeah, then it should be adding FFFF to that. Oh, so that's what we got to do with the branch. So on the branch instruction, we needed to enable this right here. And that needs to be done from the control line from the from the birch. So the control line from the birch. So control line from the birch for the branch instruction. Okay, okay. What instruction? So yeah, it's swapping off the most significant bit, but it doesn't know what instruction we're doing. That's what that line is. So we need, I see. Okay. Alright, so this line will be that the branch is true, and with the branch being true, we need to then tell it what operands to take. Should be this right here. do I get this to interlock? Just like that. I don't know where that purple line thinks it has to go as well, but and there. So now we're telling it around that instruction, so it should take it needs to as well as tags. And we don't want backfill on that, so we only want to go that way. And now it does that. So now we say, hopefully this is synced and it says either put nothing on the bus, nice, or put what I freaking want on the bus. Nice. Okay, and now it's putting what I want on the bus, and now on the output here should be 0, because 1 plus negative 1 is 0. Perfect. Lovely. We have just computed a branch calculation, boys and girls. Mostly boys watching this. Mostly men. Alright. Okay, how's your exam going? You still watching? Okay, so we've done our 3-operand branch and got that to compute. Now let's do our 2-operand. And now we're going to say, if it's greater than 0, we're going to branch. We're going to put a 1 on the line. So it's greater than 0. Comes down that way, tells it what it needs to do. Tells it oh yeah, with the branch we want to do that. Yeah. So now we're telling it with greater than 0 if it's true. We need to then take, so we need to do the same thing. So that's really easy to do for this instruction, for the next instruction. The next instruction right here. Because that obviously will reach there. All you have to do is go like this, and we'll tell it to do the same thing. To generate those same condition codes there. because the device that's telling it whether it's true or not to take the branch is different. We're just selecting the different device, but the format for the branch is the same. So like the rest of the bits are the format. These bits are which selection we take. How's it going, Oi? Thanks for joining. Any questions on anything? We currently have implemented 13 instructions. We're working on the 14th one. So that instruction is implemented. Shoots down here. Okay, so I think we're good. And that's calculating the which branch is about 1 plus -1 is 0. Okay. Cool. And now if I told it like the condition was different, so if instead of greater than or equal to 0, it's less than or equal to 0, it should now not take the branch. So this is off. Yeah, that's janky, but that'll work, I guess. That's not the this just needs to be controlled by whether or not we're branching around those instructions. Yeah, if we're on branch instructions, this is where this should be coming from, because the branch is then relative. So this should come from the branch instructions. Which are these ones. Yes. And this comes from the white stage, the birch stage. Is that too soon? Is that too late? Yeah, the birch stage calculates. Yeah, okay. Yeah, it's got to come from the birch stage. Yeah. Okay. Beautiful. Whoops. So if we're on a branch instruction, then we have to be telling it to do this. And whether or not it puts the 1 on there to take it is a different story. This is whether or not it should take the calculated branch. It should calculate it, but whether or not it takes that calculated one, that is the proper way. A little less janky. Okay. So I think we have all of our jumps implemented. Well, yeah, we have, because I know I did jump and links already, and I got it to right back. And we just did our branching. So we've gotten all of 4 jumps, all 4 branches, even though they're only encoded as, well, yeah. Each one takes 2 instructions, but we have 8 instructions out of it. Alright, so this thing is getting more and more further along each second. We're skipping instruction 14, that's reserved. To be frank, I don't know what I need it for. I just figured I'd rather leave it blank than encode a stupid instruction that I don't really need right now. But like, I guess if a user downloads the CPU, they can put whatever instruction they want in instruction 14. It's on them. It would be easy to modify the assembler to add whatever instruction you want. The assembler is really, really nice. It's really powerful. But now we have to implement the load store, and this is what's going to take literally the rest of the stream, guys. We need to build addressing for the RAM, the memory mapped I/O, and then we need to get the instruction encoded. So we need to define where the memory map is going to be and where the memory space is going to be. So I really have a 15-bit address worth of RAM to work with. This is Minecraft. We're never going to need that. So I was okay sacrificing 1 bit for like, because like, you know, obviously everybody wants like some power of 2 for addressing. Like 16 bits or something like that, not 15. But I was okay sacrificing 1 bit because I know this is going to be in Minecraft, and 16-bit range is ridiculous, 15-bit range is ridiculous, and anything probably over 10-bit range is ridiculous. So the goal here is what I'm going to do is I think I'm going to have the low 12 bits will be reserved for memory. The moment you put a 1, so like if you're talking in hex, 0 0 0 0 to I want to format this. Format plain text 0 0 0 0. Then in hex, then this would be 0 f f f. So I could say from 0 0 0 0 is the base of my memory map, and then base RAM address, and then I could say this is max RAM address. Obviously you're never gonna have 2 to the fucking, what is that, 12? You're not gonna have 4096 words in Minecraft, like some reliable amount like that. Like that's quick enough to actually do anything in a 20-tick pipeline without a million load stalls or something like that. Like it's just not going to. So that's just like what I'm gonna do, like, because it just makes it easy. So like in theory you can hook up more RAM, like you can just keep adding RAM to this in Minecraft. Like you're not gonna run out of addressing space to hook up that RAM. You have 12 bits of addressing space. Now what I'm gonna say is we go from 0 0 ff. The moment you go 1 0 0 0 to f f f f, that's the base of MMIO to the top, or to the max MMIO. So for instance, now all I need to do is check if the top 4 bits are greater than 1. So I OR the top 4 bits together and then use that as a flag. And if those top 4 bits are greater than 1, then I'm in MMIO, else I'm not. Because you're never going to be even that high up. So, so like the idea here is, if you're using, if there's 31 or 32 memory maps, memory map in and out ports, you would say like 1 0 0 0, or like this is, you know, number 0, and then the max would be 31, which would be FF, I think. No, that would be 64. No, 3F. 3. What the hell would it be? What is 31 in hex? Yeah, 31 in hex. I'm so dumb. What is it? 1F. There it is. Duh. Yeah. Okay. So you'll have max of, so if I have, so I'm gonna say 1 0 0 0 through 1 0 1 F. Oh wait, shit. 1 0 1 F. So 2. So I am only going to have 32 ports, so 0 through 31 is going to be my memory map. So you're just going to make sure you have a 1 as the topmost nibble, like that, to make sure you're addressing memory map instead of RAM. Whoops. So now I'm going to say, for my RAM, I have 128 words. I'm going to designate 64. I'm going to designate half of that to being stack. Which I think is okay. If I had, I can get away with using 32 if we don't want to do like a whole bunch of nested subroutines, but I kind of want to be able to do a bunch of nested subroutines. Also, like, the reason, like, in MIPS, everything is byte address, so it looks like they're using a lot of RAM because everything is byte address, so they have to use like 4 times the amount of RAM. But because their word size for 32 bits, so 32, 8 times 4 is 32. My word size is 16 bits, and it's byte, it's word address, so I have half the data, but it only takes one memory address to hold it, versus they had 4 times the data, or twice the size in data, and it took 4 memory addresses. So there's like trade-offs and stuff like that. So like I don't have to use as much RAM to access subroutines and stuff like that as regular MIPS. So like I could probably get away with just giving 32, or maybe I can fuck it. What about like some weird number like 48 or something like that? So like whatever, 128. What is equals 128 minus 48? 80. So I could say I have 48 lines of stack, 48 words of stack, and then 80 just like RAM addresses. I think that would work. So I wonder what alright, so we have, so we're really gonna say 0 0 0 0 this is gonna have to all be moved down. Zero 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 to what is 128 or 127? How 1 2 3 4 1 2. Oh wait, no, this, yeah, 255. So yeah, hex FF. Okay, but that's not what I have. I have 1 2 3 4 1 2 3. That's what I have. So I have 7F. So 0 0 0 through 0 0 7. f is going to be really going to be my max RAM address. I have 128 words of RAM. So even though theoretically my max is this in terms of addressing, the max that's connected is that. So max in addressing actually connected. Alright, so it's like a column. So all these going down is a column, and then all of these going down is a column. And I guess I should there. So that's the max RAM, and I'm gonna say then the top 48, so 7FF or 7F, 127 minus 48. What if I just designate 0 through 47? What is 47? It's that. Fuck. So checking for 48. It's just so easy to check for a power of 2. Yeah, so I think we should go for half, 64. First, well, it would be 63. So that's 3F. So we go 0, 0, 0, 3F, and then 0, 0, 4, 0. Oops. Why isn't it formatted? Format number. And then we go 0040 to 007F. So this is going to be the top of stack. This is going to be the base. No, maybe we should reverse that. We'll make that base top of stack. Oops. I'm not sure which way I want to implement this. This may change a few times. And then just base. Okay, so now you can say your stack is from 0000 to 003F in the RAM, so your stack pointer will be in that range. Hopefully always less than 3F. If your stack pointer ever is larger than 3F, then you have a problem. So that's how we're gonna define, just like for ourselves in software. That's not gonna connect anything hardware wise. And then we're gonna say then 101F. Base MIO top base of there we go. Okay. Okay. I think we're ready. Okay. All the RAM has decoders for itself. I'm designating the low 12 bits for RAM. So 1, 2, 3, 4. Now I'm going to say if these bits get ORed together, I only want the top 4. 1, 2, 3, 4. 1, 2, 3. Okay. And so now, let's see what signal strength I get out of that. So 4, 3, 2, 1. Let's do it there. Oops. Why did I do that? I'm so confused. Yeah, let's do it over here. Seven, 6, 5, 4, 3, 2, 1. Nine, 8, 9, 8, 7, 7, 6, 5, 4, 3, 2. So when this is true, this is when we memory map to the IO. Okay. Okay. World edit. So I can pass this through, and this is going to tell me that I'm actually going to be using this. So the enable here, the enable logic is going to be if we're on the instruction and on the MMIO, then it gets the address. So it should probably encode 15. Guys, I think I gotta get going, but I think I also gotta stop and think about how I want to encode this load store a bit more. So I think this is gonna be at the end of the stream. I might stream again later today, but I might not. But yeah, thanks for watching if you guys are still here, and I'll see you guys next time. Peace.